Hey there, everyone. Welcome back to this Introductory Cosmology course. We're on Chapter 2, and we're talking about fundamental observations, and we're going to be talking about this Olbers Paradox. The night sky is actually dark. If you're just tuning in, this is your first time in my cosmology course, please make sure to watch all the videos in the series in the order that's in the playlist shown below, and that way you can get the entire experience and get everything in the correct order, because this is a college course following a textbook. So also, please subscribe to the channel so you'll be notified when the next video in the series is released. And with that out of the way, let's get to it. Since we wish to understand the cosmos using science, we need to observe it and try to understand our observations using known physical principles. And as we make our understanding, it's critical that we discard ideas that cannot be supported by observations. We also have to follow known physical laws, and any models that we describe must have observationally verifiable consequences. Otherwise, it's metaphysics, or worse, just useless blather. So we'll need to start to understand the fundamental observations. There are 4 that we're going to cover in this chapter 2, and the first one is the night sky is dark, Olbers Paradox. And that's kind of a funny thing to say. It is actually odd that the night sky is dark, because logically, according to many theological ideas and, quote, common sense, it should be filled with stars. The night sky is dark. Obvious astronomer is obvious, obviously. Or is it? Go outside at any time when it's truly dark, no clouds, away from city lights. You see mostly dark sky, optically, punctuated with a few thousand stars. That the night sky isn't uniformly bright as the surface of the sun is actually our source of our first concern. It is this observation, that the night sky is dark and isn't the brightness of the sun, that tells us a lot about the universe as a whole. And that we even have night at all is called Olbers Paradox. In 1823, Heinrich Olbers published a paper that asked an incredibly simple question. Why is the sky dark at night? Olbers, he reasoned that if there were an infinite number of stars in the sky, then no matter where we look in space, our line of sight should eventually terminate in a star. So the sky should be everywhere bright. That logic is sound, but the sky is not bright at night. So what's the deal? Now, Olbers' idea didn't come out of nowhere. When Copernicus developed his heliocentric model in 1514, he relegated the stars to a celestial sphere of extraordinary distance. But this idea was extremely controversial, and it was controversial enough at the time for him to wait to publish it after his death in 1543. Further, when De Revolutionibus Orbium Celestium was published, it contained an anonymous, unauthorized preface by one of his fellow theologians and a good friend, and it was designed to obviously soften the blow with the Catholic Church. The preface that this person put was stated that Copernicus wrote his heliocentric account of the Earth's movement as a mathematical hypothesis and not an account that contained any shred of truth or probability. Copernicus's idea contradicted the Old Testament's account of the sun's movement around the earth in Joshua 10:12-13. However, there was no evidence at all that Copernicus himself considered the heliocentric model as merely mathematically convenient or separate from reality. He was just being a smart rabbit and trying to make sure his idea got out there, but that he wouldn't face excommunication. That's why he published it after his death. And that it was published at all was a testament to his good standing as a theologian and church leader. It also testifies to his reputation as a sound thinker. The upshot of his work, though, is that the sky was broken by a moving earth. Only 30 years after Copernicus's death in 1576, Thomas Digges published a new edition of his father's astronomical almanac, and he has published a bunch of appendices with it. And the most important of them was called A Perfect Description of the Celestial Orbs to the Most Ancient Doctrine of the Pythagoreans, lately revived by Copernicus and by geometrical demonstrations. So his father's original book, his father's almanac, was proposed the Ptolemaic geocentric cosmology. But the appendix that Thomas Digges put in there detailed a discussion of this controversial and still poorly known Copernican heliocentric model for the universe. And in fact, this was the first publication of that model in English, an incredibly important thing in the popularization of science. Thomas Digges's appendix was really just kind of a loose translation into English of some of the chapters of Revolutionibus Orbium Celestum. But in particular, he stated, this orb of stars fixed infinitely up, extends itself in altitude spherically and therefore immovable, the palace of felicity garnished with perpetual shining glorious lights innumerable, far excelling our sun both in quantity and quality, the very court of celestial angels, devoid of grief and replenished with perfect endless joy, the habitable for the elect. Wow, that's some amazing stuff to say. There are stars going out to infinity. Thomas Digges therefore extended Copernicus's idea by proposing that the universe was infinite and contained infinitely many stars. And this idea predated Giordano Bruno. It was in 1584 and William Gilbert in 1600. Copernicus, taking the Earth out of its special place, which really wasn't that good of a place in medieval theology, he had opened the door for an infinite universe. So with this in mind, how bright should the sky be in an infinite universe? Well, let's note what the rough number density of stars are that there are in the universe, and that number, which I'm going to note here with n sub star, is approximately 10 to the ninth stars per cubic megaparsec. That's a lot. So it's about 1 billion stars per cubic megaparsec. That takes into account the idea that galaxies are hubs of stars, but they're not distributed evenly. We're going to pretend that we don't know galaxies exist and that stars are distributed evenly throughout the cosmos. That would be fitting for this time period and this early of Olbers' idea. Now let's get the typical radius of a star, and we'll determine that to be just like the sun. Well, we could use any old value, and since we know that red dwarfs make up the vast majority of stars, we could use that, but for simplicity's sake, let's just use the sun. And it won't alter our eventual result except by maybe a factor of 2 to 10 or something, but it won't change the real result. So if we take the radius of a star, which is approximately the radius of the sun, that's about 7 times 10 to the 7th meters, or if you will, 2.3 times 10 to the minus 14th megaparsecs. Stars have really small radii when measured in megaparsecs. All right, so now let's look out into space and we make a cylinder. If we make a cylinder with radius r star, and we make that very, 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 very long cylinder, how many stars will be in there? And that is given by the number capital N, which is the same as the volume of the stars, volume of the cylinder V, times the number density of stars, N sub star. And the volume of a cylinder is, of course, lambda pi r squared, where lambda is the length of the cylinder and pi r sub star squared is the one of the circular ends of the cylinder. And that gives us the total number of stars that are in that volume. So when we look out through such a volume, we're going to see stars. Now we only need to see what the volume of the cylinder is for one star to be in the way on average. So let's set that big capital N equal to 1 and solve for that for the length of the cylinder, because that's really what we're trying to say is how far can we see? And so the length of the cylinder is lambda, and that's equal to 1, where the 1 is now meaning 1 star per volume, which is out of the number density times the radius squared. Pi r squared times that number density. So really what we're turning is a volume density into a surface density. Again, we're going to use n stars equal to 10 to the ninth cubic stars per cubic megaparsec, and pi r sub star squared is approximately pi r sub sun squared, which is in units of megaparsecs, about 10 to the minus 27th square megaparsecs. So it's a really tiny aspect of a megaparsec. So lambda then, when we plug these numbers in, is 1 over those two numbers combined, and that gives us 10 to the 18th megaparsecs. So that's a distance. That's a really long distance. So 10 to the 18th megaparsecs is really quite big. but it's not infinite. And for comparisons of numbers to show how finite this number really is, the total number of cells in your body is about 36 trillion, or about, we'll call it 4 times 10 to the 13th. So the total number of human cells in a medium-sized American city is about 10 to the 18th. That's definitively finite. Still, 10 to the 18th megaparsecs is much, 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 much bigger than the Hubble length. This means that if the universe were at least that big in radius, then we should see a star in every direction we look, and the sky would be paved with stars. Now we have to ask the question, how bright is this paved sky? Doesn't the brightness of some light source dim with the distance? It does, but these stars are not points. They have an area, so we need to translate that area into some angular size. And it's not just a linear angular size, but an angular area. Angular areas are measured in steradians. There are 4 pi steradians of angle on the surface of any sphere, as viewed from the inside. From the center of the sphere looking out, there are 4 pi steradians. So if the star is really, really, really far away, then you can be considered to be a flat disk on the surface of our angular measuring sphere. And so then we get this omega equals pi r star squared over r squared. Omega is the steradian angle from which the light is coming to us as seen in the sky. The physical area of the star is pi r squared, so r star squared. That's the profile that we see, the physical area. And the distance to the star is little r squared. That equation is pretty good when the star is really far away, and you can approximate half of a sphere of a star with a disk. So thus it subtends a very small aerial angle. And a star has a given luminosity, and the flux will be the luminosity distributed over the sphere at some distance from the star, and that flux is usually F, and that's equal to L sub star, the luminosity of the star, divided by 4 pi r squared, where r is the distance from that star, and flux is measured in joules per second per unit area. And that's usually per unit area on the surface of a sphere that is centered on the source of the luminosity. Well, that distance can be from the star, whether it's in 10 meters or 10 astronomical units or 10 to the 18th megaparsecs. Now, the surface brightness of that one star is measured in watts per square meter per steradian. Now, the area might be the pupil of your eye or a primary mirror of some big telescope like the James Webb. Surface brightness is the relationship between how the light is distributed from the source out to some distance and the size in the sky we see that source to be at that distance. Flux is power spreading out from the source to the observer, and the angular size is the observer seeing how big the source appears to be. Now, it could be that you're making the mistake that the surface brightness is how bright is the surface of the sun or whatever. That's luminosity. This surface brightness is the brightness on the surface of the celestial sphere, meaning our view of the entire sky. So the surface brightness of the one star is the flux per steradian, and that's what the sigma is. It's usually used as surface brightness. So sigma sub star is equal to the flux F divided by omega, which is the steradian angle. And we can see that we plug in those two other things before, and we end with L sub star divided by 4 pi squared, r sub star squared. All right, what's really interesting here is that the surface brightness does not depend on the distance to the star and only the star's luminosity and its radius. So the surface brightness of an infinite sky paved with stars, or at least a universe 10 to the 18th megaparsecs in any direction, will be as bright as the disk of the sun. This, of course, is complete bonkers nonsense, as you can totally understand. Well, it's not just that it sounds bonkers. How bonkers is it? We need to quantify our bonkerhood. The surface brightness of the sun, sigma sub sun, is about 5 times 10 to the minus 4th watts per square meter per arc second squared. And the surface brightness of the dark night sky is 5 times 10 to the minus 17th watts per meter squared per arc second squared. And so Our estimate is off by a factor of 10 trillion. So we got to have something wrong with some assumption somewhere. And let's look at all those assumptions and see where we went wrong. Okay, our assumptions are the following. 1, the universe is completely transparent. 2, the universe is infinitely large. 3, the universe is infinitely old. 4, the surface brightness of a star is independent of its distance. And 5, light doesn't lose any energy as it traverses the static universe. Let's look at each in turn. First, let's look at the transparency. Okay, so let's say the universe has something blocking it. And originally, that's how a lot of people thought this would be resolved. So that opaque something would absorb that light because it's absorbing it because it's opaque. And eventually, over time, something that's opaque will heat up. And therefore, the thing that's in front of all that starlight will eventually heat up until that thing is just as hot as the ambient starlight. And therefore, you have the same problem over again. So it doesn't matter whether it's completely transparent. In fact, that doesn't work at all. Next, the universe is infinitely large. Let's look at that one. If the universe has a finite size, let's just pause it for just a second. If it has a finite size, then only a fraction of the sky would be covered. Let's say the universe is literally a box and whatever's outside the box, we don't know, we don't care. So the fraction of the sky would be covered because there's only so many stars inside a finite box. But if it's infinite, but past that point there are no stars, okay, well, that's the same kind of thing as if it's infinite, but there's nothing past that. And then we would be just happening to live amongst the only island of stars, which seems a little weird. So there's some things that could be wrong with it being infinitely large. Next, let's look at the assumption of the infinite age. Well, perhaps we can violate that by saying we live in a really special time, in this ageless time where stars truly now exist. And before then, they didn't. Or if the universe has a finite age where, say, some t sub naught, that's the finite age, is much less than the size, lambda, divided by the speed of light. If that's the case, then due to light's finite speed, we could only see stars out to some maximum distance, r, which is about the speed of light times this age, t sub naught. And only some fraction of the sky will then therefore be covered, which would be f, would be that fraction that's roughly the same as the speed of light times the age of the universe divided by the distance of the universe. So that'll be some fraction of the universe would be covered. Next, we have to look at the surface brightness of a star being independent of its distance. In an expanding universe, the surface brightness would drop with distance compared to a static universe envisioned of an infinite static universe. And if we're contracting, things would be brighter than expected. So maybe this expanding universe will get rid of it too. Next, let's look at light not losing energy as it traverses the universe. Okay, so it does lose energy due to the cosmic redshift, but let's say you believe the universe is not expanding. So light maybe would get tired as it travels and lose energy. And this tired light idea is kind of new, and it's not at all supported by observations. First, tired light can't replicate the blackbody spectrum of the cosmic microwave background. Without the expansion, every photon in the universe must lose energy in a way that preserves the perfect blackbody spectrum. This is kind of improbable, since every photon would have to know what every other photon is doing in the entire universe, and that's kind of a big call for 10 to the 89th cosmic microwave background photons. All right. So also, tired light can't explain the time dilation of high redshift supernovae. If tired light was a thing, then the light curves of supernovae would be distance independent. And they're simply not. They're stretched out. The farther away they are, the more stretched out the supernova light curve is. Next, tired light would change the photon's momentum and blur distant objects because if you change the energy of a photon, you do change its momentum. And momentum has a directional component. So therefore, it would blur the distant objects. It's not seen. So tired light would also alter the surface brightnesses of galaxies in a way that's not observed, i.e. making them distance independent. This isn't seen due to the expansion of the universe that we know exists. So how is Olbers' paradox actually resolved? And I'm just going to give it away. The resolution is principally due to a finite age of the universe. The light from the horizon distance simply has not had time to reach us yet. And the horizon that I'm talking about is not a boundary or an edge. It's not something that if you went up to it and you would fall through or punch through. It's not this depiction from the 1888 Flammarion engraving. This kind of edge boundary simply does not exist. Um, it's just the place from which we've been able to get light. So that's what we mean by the horizon distance of the cosmos. The currently understood horizon distance, I'm going to use Planck mission's value for the Hubble constant, which is 67.8 kilometers per second per megaparsec. And that gives us a horizon distance of approximately 14.42 gigalight years, or about 4.4 gigaparsecs. And this distance is, of course, a lot smaller than infinity and a lot smaller than 10 to the 18th megaparsecs. Yeah, I kind of alluded to Hubble constant. We'll get into the Hubble tension later. Just to close this thing out, it's kind of funny that in 1848, Edgar Allan Poe chimed in with a correct interpretation from his Eureka, a Prose Poem. No astronomical fallacy is more untenable, and none has been more pertinaciously adhered to than that of the absolute illimitation of the universe of stars. Were the succession of stars endless, then the background of the sky would present us an uniform luminosity, like that displayed by the galaxy, since there could be absolutely no point in all that background which would not exist a star. The only mode, therefore, in which, under such a state of affairs, we could comprehend the voids which our telescopes find in innumerable directions, would be by supposing the distance of the invisible background so immense that no ray from it has yet been able to reach us at all. Well, that raven didn't need to speak too much more on that topic, now did it? Well, so much for the night sky. There's a night sky, and we can solve it by understanding that the universe has a finite age. I'd like to thank all my Patreon supporters for their support. It's been great having their help in this and their support, and I hope you would like to become one too. In the meantime, please subscribe and like this channel and like this video, and please share it around, because I'm going to be doing the entire textbook from Dr. Barbara Ryden's Introductory Cosmology, and this is just the second of many innumerable videos I will be doing on cosmology from this textbook. And we'll see you next time.